correct. These were right. This third question was also right. This was also correct. Ibrahim, in the fifth question, see, I gave this as a homework also. When you have to write the dipole moment, you know, dipole moment is it's a vector quantity, so you need to mention the direction by yourself. See, be on the safer side. You don't know how the marking scheme is made in your final board exams, so just write the direction because it's a vector. Vectors are always incomplete without directions. Have a habit of writing two things. One is the SI units wherever you are, in whichever question you are attempting. Second, if it's a vector, then direction. Otherwise, your paper was very good. You've done everything correctly except the last derivation. This question we discussed in the class itself, the not the ninth one. One derivation, this sixth one. See, Ibrahim, this derivation was incorrect.
Yes, ma'am. I knew that, but I ran out of time by the time I reached there. Yeah, because
Okay.
I left it for the last, so I ran out of time. So like I couldn't
Okay.
do it.
So just check this because derivations are important and derivations are very scoring. Okay, let's continue
Yes,
today's class also, and let's not waste much time. Let us continue with the class now. So that's why I wanted to discuss the paper. Now let us come to our class. So we were discussing continuous charge distribution. All of you give your assignments also. There are good questions from this continuous charge distribution. Some questions are difficult also. We'll discuss them. Let us complete this chapter. Not much is left in this chapter. And those who have the exam, Zainab and all, they can at least attempt the derivations. We discussed continuous charge distribution basically had three things: the linear charge distribution, the superficial, and the volume, right? So in the linear one, you have the charge per unit length. In the superficial, you have the charge per unit area. And in the volumic, you have charge per unit the volume. Now, before we begin with the derivation, you need to understand that every surface is not closed for you. Okay, many of the surfaces are open. Open as in, like if a wire is present and charges are present on the wire, then we'll say the wire is open completely. It is not a closed surface. So for any application based question of Gauss theorem, we need to first construct a Gaussian surface. That is, just construct a hypothetical surface around the wire or any surface that you have, whichever is suitable. Like mainly you have a cylinder, a sphere, or a Gaussian pillbox that is taken. Gaussian pillbox basically means rectangular cuboid, basically cuboid is a Gaussian pillbox. Second is cylinder. Third is this. So these are important for you should know. Now, remember, if you have a wire, the preferable, if you have a, suppose this is a wire, the preferable Gaussian surface around will be a cylinder. The cylinder will cover it completely. All the charges will be on the wire and the cylinder will completely cover it. So for a wire, we prefer a cylinder. For a sphere, we prefer a sphere only, but a sphere with a greater radius, which can cover our sphere. And Gaussian pillbox is hardly used. These two are enough for our derivations for this time. So you have a Gaussian surface, which is a geometrical shape. This is a hypothetical concept just to make our charge enclosed. So the radius of the Gaussian surface will be considered. That we'll take it as R. Suppose this is a wire. It has charges and it is extending from infinity to minus infinity. Okay, this is extending from plus infinity to minus infinity. Now it has charges. So in order to enclose this wire, we have covered it with a cylinder completely closed. Now, this is our Gaussian surface. Its radius is small r. When we have small r is the radius of the Gaussian surface. No, not always sphere. It should be just enclosed. Zainab, you forgot to take the notes on that day. You also left the meeting. Just remember, you have to take the screenshots today, Zainab. Gaussian surface need not always be a sphere. If it's a sphere, then you take a bigger sphere because spheres can be covered with the help of bigger spheres only. But if it's a wire, we have taken a cylinder here, so it is not always needed to be a sphere. This is a cylinder whose radius is r. So the r is the radius of the Gaussian surface. R is the radius of the Gaussian surface. Okay, this is the radius. Now class, Again, when it comes to a cylinder, you have lots of questions on cylinders in your Gauss theorem already. So let's take the area vector. So when you have a cylinder, see the top surface is curved. Suppose this is the top surface for it. So electric field is towards the left side, right side, right? Electric field is towards the right side. When I take area vector perpendicular, see here we are getting 90 degree. So here the cos theta, this will be our n cap, and electric field is here. It will be 90 degree. This is the first surface. Come to the second surface like this. See, the curved surface is like this. The electric field is still towards the right side. You take the 90 degree, you take the area vector perpendicular to its surface. See, this is still making an angle of 90 degree when it is taken perpendicular to the surface, right? So this second surface, area n cap will go below. Electric field is already like this towards the x-axis. Why x-axis I'm saying? Why only x-axis I'm saying? Because see, wherever is it, even if we take it on the left hand side, any side, as soon as the area vector comes, it will always be 90. So you take it on the opposite side also, you will get it as 90 degree. So due to first and second surfaces, we won't have the flux. Now, third surface, even if I take this surface or I take this surface, I will get the electric field value. So let us come to the calculation of the electric field now. According to our Gauss theorem, electric field dot ds, close integral of electric field into ds is what we are getting. Now, when you have the flux present, flux is equal to Gauss, according to Gauss law, we are going to put the value of flux. We are going to have this value, and then we are going to equate both of it. Okay. Now, when we are talking about the cylinder right now, electric field is constant. So electric field will come out and I'll be left with surface integral of this. So surface integral, I've told you, don't integrate or do something else. Whatever is the surface area of the entire figure, take it as it is. We have done it before also. So this will be E into 2 pi r L. L is the length of the cylinder. Okay, I'll write it here. L is the length of the cylinder. That is our Gaussian surface basically. So this is the value of flux. Now flux according to Gauss law is Q by epsilon naught also. This is according to the Gauss law class. Gauss's law. So class, this is also a value of flux according to E dot ds. This is also the value of flux according to the Gauss law. So it means both of these values are giving me the values of flux only. So I can equate these two equations. So see, when this and this is, both of these are equated. E into 2 pi r L is equal to Q by epsilon naught. Now for a wire, class, which density should be better? Continuous charge density, which should be better out of all the three that we have discussed for a wire? A wire, charge is distributed on a wire. Should I use linear, superficial, or cubical? Superficial. No. See, it will be linear because wire is a straight line. I told you when you have one-dimensional figure. So in those cases, you take the linear charge density. Linear charge density means you are talking about the charge per unit length. See, is the charge distributed over the area or over the length? This is a wire. It is distributed on its length. So you are going to take the linear charge density. Lambda is Q by L. So Q will be equal to lambda into L. Let's put the value of charge here. E 2 pi r L is equal to, charge is lambda into L by epsilon naught. Length gets cancelled. So what's the value of electric field? See, electric field is coming lambda divided by 2 pi epsilon naught r. This is the electric field due to a straight wire. This is the derivation of it. Derivation is very important, class. What are all these terms? E is basically the electric field. Lambda is the linear charge density. 2 pi constant epsilon naught, you already know its permittivity. R is the radius of the Gaussian surface. So how will you determine this in the numericals? It will tell you there is a straight wire with some charge on it. Calculate at a point, let's say 10 meters from it. So you will make this as your Gaussian surface, this hole. So your radius will become this 10, whatever is the point given, like this. This is how we'll construct. So tell me, class, this first derivation is clear? Clear or not? Ibrahim, Jasleen, Zainab.
Yes, ma'am.
Okay, write it down. Class done? See, the next derivation, before the next derivation, let's see a question. In the center, when you have both the wires present, so this is the positively charged wire, this is the negatively charged wire. So at the center, see, we are calculating the center is separated by both the wires at an equal distance d. This is positive, this is negative. So see, we'll see the direction first. At this point, due to the positive charge, means the first wire, electric field will be pushed away. This is electric field 1 due to the first wire because it is positive. So electric field is going away. Second, you have the negative wire, right? And for negative wire, we know electric field is towards it. It means at from point O, I'll have to move towards the wire second because this is towards the negative wire. So if I go towards it, it will also point like this. So electric field second will also be in the same direction as that of the first one. So class, when you're calculating the net electric field here, the net electric field will be E1 plus E2. Now both are wires. So we can use the formula. Lambda is also present for both of it. Lambda by 2 pi epsilon naught D plus lambda by 2 pi epsilon naught D. So this will be straight away 2 lambda by 2 pi epsilon naught D. So look here, 2 will get cancelled. The net electric field will become lambda by pi epsilon naught into D. This is the electric field, net electric. Okay, we'll see the next derivation due to the plain sheet, but just before that, write down this part. And if anyone wants to ask anything, please let me know so that we can complete this chapter. And if you have any queries in between, please tell me and just text me done once written. Is it clear? This question is clear to all of you?
Yes, ma'am.
Class, see here, we have now an infinitely plane sheet. So what is the meaning of infinitely plane sheet? Basically, the sheet is extending up to infinity. It's a very, very big sheet. So we have just taken a small portion from that sheet. That's why the edges are not very smooth. These are curved like this, because there was a big sheet that is infinite, extending up to infinity. We have just taken a portion of it because of our derivation. So class, what we'll do, since see, we cannot accommodate the whole sheet. So what we'll do, we'll just take a small portion using a cylinder like this. A cylindrical portion we'll take, and if this is a positively charged sheet, electric field will be on this side. Now we'll again calculate all the things similar to what we did in the previous case. First will be this, second will be this, and third will be this. Now class, here we'll see the direction of our n cap. Now see, this time n cap is not situated like this. The sheet, the curved part of your cylinder Gaussian surface is put like this. So now when the electric field is in this direction for it, look, this is the electric field, this is it. So it is in the same side, making an angle of 0 degree. So this will be 0 degree for it, right? This is n cap. Similarly, this side also you will have n cap, and of course this side also electric field will be in its direction. For the positive one, it will be away from this side. So for these two sides, we'll have the electric field. But class, for the curved part, see, for the curved part, the area vector is above. So electric field is pointing in either side. So it will directly be 0 for the second part. So electric flux for the second part will be Es cos 90 degree. That is 0. Now flux will be, the net flux will be due to the first surface plus flux will be due to the third surface class. Now look, what is the first surface? This one, right? So it is Es cos 0 degree plus this is also Es cos 0 degree. So flux is simply Es plus Es, flux is equal to electric field into 2 times electric field into surface area. Now we'll use our Gauss theorem. We know the flux is charged by epsilon naught. This is according to our Gauss law. This is according to the Gauss law. Flux is 2Es, right? Es plus Es, that gives us 2Es. So this is 2Es. And flux is also Q by epsilon naught. So it means we can equate both of these. 2Es is equal to Q by epsilon naught. Now tell me, for the sheet, which surface charge density should be applicable? Linear, superficial, or cubical? If it's a sheet. If it was a wire, we took the linear. This is a sheet. Yes, enough. Now it's right. Superficial means charge per unit area. So the superficial sigma is charge per unit surface area. So our charge will be equal to sigma into surface area. Let's put this value here. 2Es is equal to sigma S by epsilon naught. S gets cancelled. Electric field due to the plane sheet is sigma by 2 epsilon naught. And when you plot the graph, see here, you are not getting any radius. In the previous case, you were getting the radius, right? The electric field was inversely proportional to the radius in this question. In this case, E was inversely proportional to R. So if you had to plot a graph, this would have been the graph. This is R, this is electric field, E versus R graph. But see, in this, radius is cancelled. So you don't have the radius. So this is how independently it will look like. What is this? This is the electric field. What is sigma? It is the surface charge density. That is superficial charge density. And epsilon naught and 2 you already know. Now class, how the questions can come in this? There are only one set of questions that can come. If one sheet is there, you will be able to manage. This is the formula. E is equal to sigma by 2 epsilon naught. Class, it can give you points like this. Suppose these are two sheets and this is a point where you have to calculate the net electric. So see, electric field due to the positive one will be away, E1. Due to the negative sheet, electric field will be towards it. So you know electric field, both the electric fields are in the opposite direction. So what you do for the net electric field, E1 and E2, they are in the opposite direction. So you just write them vectorically. Just put Cartesian form. For the time being, I'm using it. If in the question values are given, properly put the values. Sigma will be given. Epsilon naught you already know. Only you need the values of sigma. That is the superficial charge density. So here E1 will be sigma by 2 epsilon naught. This will be towards the negative x-axis, minus I cap, plus this is sigma 1. Yeah. Due to the negative wire, it will be not wire. Due to the negative sheet, it will be sigma 2 by 2 epsilon naught. So this is towards the positive x-axis. So this will be I cap. Look what I've done here. At the net point, at this point, we have to find out the net electric field at this point. So due to the positive sheet, the electric field is going away. E1 is away. That is towards the negative x-axis. So what you can do, you can directly write like this also, sigma 2 by 2 epsilon naught minus sigma 1 by 2 epsilon naught, because both of these are getting subtracted. They are in the opposite direction. But for the time being, for this question, I have just put I cap so that you know the directions. Otherwise, you can use it like this also. And then calculate your net answer. Take 1 by 2 pi epsilon naught common into sigma 2 minus sigma 1 like this. Is this clear, class, to all of you? Yes or no?
Yes, ma'am.
Yes, ma'am.
Ibrahim, clear?
Yes.
Okay. Now, if I give one more point, let's say in between somewhere here we have the point. Now, when we are calculating the net electric field, see, due to the positive sheet, it will be away. E1 will be away. Due to the negative sheet, it will be towards it, E2. So now when we are calculating the net electric field due to the second point, see, electric field will be, both of them are in the same direction. So they'll directly be added, sigma 1 by 2 epsilon naught. But still I'm writing the Cartesian vectors, unit vectors, so that for the different kinds of questions, you know how to handle them. So this will be sigma 1 by 2 epsilon naught. Both are towards the I cap, plus sigma 2 by 2 epsilon naught I cap. Directly you can write like this also, sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught. Solve it when the questions give you values. Third point, can we see here we calculated it here in the middle of both the sheets. Now another extreme point can be if I take this side of both the sheets. Two sheets are given. This is a common question and this is the toughest question that is possible. So that's why we are discussing this from your plain sheet. Now for the positive sheet, electric field will be away E1. For the negative sheet, it will be towards, like this, E2 will be towards it. So at this point, we are calculating the net electric field. Now look, the net electric field will be due to E1, sigma 1 by 2 epsilon naught towards the positive x-axis, minus sigma 2 by or plus sigma 2 by 2 epsilon naught towards the negative x-axis. So minus I cap. I've written it like this, but see, you can always like solve it like this. Sigma 1 by 2 epsilon naught minus sigma 2 by 2 epsilon naught, like this. Am I clear to all of you? Now, anything you want to ask? Anything you want me to repeat? Zainab, Shaima, Jesleen, Ibrahim?
No, ma'am.
No, ma'am.
No,
Okay.
ma'am.
All right then. Write it till here, class. Jesleen, you there? Okay. All right. Write it, all of you. Just text a done class in the chat box when written, then one last derivation is left that we'll complete. Zainab, after this derivation, the class will be finished because this chapter will be over. Okay. Let us just complete. Zainab, you have written? Zainab and Jasleen? Okay, let us just complete this. See, you have now the derivations on the spheres. So remember, whether it's a solid conducting, hollow conducting or non-conducting. For hollow spheres, the charges will always be resided on its surface. Charges will not go within the sphere. Okay. For a solid conducting, only conducting sphere, you have the charges that are present outside. There are no charges present inside. So the formula is very simple. You create a Gaussian surface. This Gaussian surface is having the radius small r. Okay, this is our Gaussian surface. Now you take this as, consider this as the Gaussian surface. This is your original sphere whose radius is capital R. So be very clear, small r is the radius of the Gaussian surface, capital R is the radius of the sphere. So E dot ds, now phi will be E into S. What is the surface area? We'll take the surface area of our Gaussian surface, not the surface area of the sphere. So area will be 4 pi r square. Then flux is equal to Q by epsilon naught. So you can equate both of these. Both of these are giving you the same flux. See, E into surface area of a sphere. It is 4 pi r square. What's the flux due to a sphere or any closed surface? It is a Q by epsilon naught. So we have considered the outer part. Now, where is the charge present? Charge is not present throughout our Gaussian surface, right? Charge is present only on our sphere, right? So when you are calculating the surface charge density for it, look, when we'll calculate the surface charge density, that is the superficial one, when you will calculate for it the 2 dimensions. Here also the charges are outside only. So we'll consider the area only. Charges are not present within the volume that we need to consider the volume. No. But where are the charges present? Are the charges present on our Gaussian surface? No. The charges are present on the sphere only. So when you take this value of sigma, that is charge per unit area, area will be of the sphere, not the Gaussian surface, because Gaussian surface does not have the charges. The charges are present only on our surface. So here you are going to take R, capital R. Small r, because this law was entirely based on the Gaussian surface. This law that we discussed, this was based on the Gaussian surface, this law. while this one, this surface area that we are talking, this is only on the sphere. So when you equate both of it, 4 pi gets cancelled. Value of electric field is sigma capital R square by epsilon naught small r square. So electric field is inversely proportional to R square. Again, you will get a graph with the hyperbolic. Now, second case is if I am taking the point on the surface of the sphere. Okay, exactly on the surface of the sphere I'm taking. Let's say this is the sphere. Okay, at a point here, I was calculating the radius. So this entire was my Gaussian surface, this entire. Now, if I reduce this point to the sphere only, so whatever is the radius of the sphere will be exactly the radius of our Gaussian surface because it will be enclosing this. Earlier, we had to take this because our point was here. Now our point is on the surface. So Gaussian surface will also be this. So when you have such a case, the value of capital R and small r will be the same this time. They'll get cancelled. So what you will get in this case, you will simply get this as same derivation. You will get it as sigma by epsilon naught because capital R and small r are exactly the same. So capital R also gets cancelled. And if we move further, now again, if we move further to the center, surface, outside, surface, and the center. In the center, there is no charge present because electric field due to solid, conducting, hollow, conducting, or non-conducting, there isn't any charge present within the surface. So straight away, your electric field will be zero because there is no charge present. So this is the case due to these spheres. Now, if I plot it, a class for solid conducting, that is not included in your CBSE syllabus. Okay, so we won't discuss that. For the students who are there in the NEET batch and all, we'll discuss there in our batches. Here, you need not discuss it. Just look at the graph. This graph is sufficient for you. Look, this is R is equal to 0. Means the center of the sphere. This is R is equal to 0. And R is equal to R. Here you have R is equal to capital R at the surface. So any point in between where small r is less than capital R is inside. This is inside from the center, inside to the surface. And if I choose a point outside, that will be small r greater than the capital R. That is outside part. So inside it is 0. So I have marked it as 0. Then exactly at the surface, we have sigma by epsilon naught, which is independent of R. And then you have electric field inversely proportional to outside. So this is how we draw. In one of the school tests recently, I don't remember the name of the school, I'll tell you. This exact derivation with the graph plotting came in the unit test, PT1. Okay. So is this hollow sphere and all this part clear to all of you?
Yes, ma'am.
Okay then. Others also or only Zainab? Jesleen, clear or not? Shaima, Ibrahim.
Uh, yes, ma'am. Yes.
Oh, write it.
Mom, can you scroll up?
Done, all of you? Others have also completed?
Yes, ma'am.
Okay, class. So this completes with the first chapter. Now in our class on Tuesday, we'll start with the potential part. Okay, so just revise integration if you all get time. Just revise the bit of integration that will be used in that chapter. And the assignment also I'll discuss. So please class attend the assignment. Zainab, it's high time now. You need to attend the assignments. Jesleen, you also told me that you will share your pending assignments. Shaima has submitted. Ibrahim is already up to date with all the assignments and tests. So please share the